Yeah, welcome back to Old School Coding. So after I shut down from the previous one, I realized that there was actually an arguably simpler data structure that I wanted to build. Very similar to the schedule. It's just a very strict little first in, first out. So you've got something that you want done, and you want to do it after other things that are already on the queue. So you've got a queue of things to do, and you run some logic and you say, well, with everything else that's queued up to happen right now is done, next I want to do this. So for example, this would be important if you have a signal going out into your system, it's fanning out and causing this to happen, which causes that to happen, which causes the other to happen. If each one of those is I trigger an edge and it runs each thing that it triggers in order, and each one of those runs each trigger, that's a depth first search of your simulation, and that probably works for most everything perfectly fine. But if your system really wants to do it breadth first, then your Fifo is your man. It's also useful if you have a bunch of things that are happening edge triggered and you've got a few things that you want to have happen after all the edge triggering has settled out. So while I don't have any specific need for it yet, I envision the need for it, and I'm going to write it up. So Fifo is going to look a whole lot like sched. So we're going to start with Fifo.h, which is going to look like sched. We're going to change sched to Fifo. We're going to change step at to step because we are not going to be keeping times on these. And apparently I didn't have the one-liner for sched. Yep. I will work that out some of the time. Let's focus on Fifo. Fifo is a list place to log and set up register things you want to do next. Okay, close enough. So it's a P step. It's not a heap. It's going to be a ring. So what I've been thinking for this Fifo is we have a ring whose size is a power of 2. And we have a producer pointer that runs around the ring, leaving valid stuff behind it, and a consumer pointer that runs around the ring, eating up that valid stuff. Now, a trick with rings, if they're powers of 2, you can keep the indexes to the full length of an integer, and you just use a mask to peel off the low bits that index into the ring. Now, if you need to expand the ring, you double its size, so you go from 8 entries to 16 entries, and you copy the first 8 into the last 8. So now the first 8 is a duplicate of the last 8. Whatever your indexes are, when you mask them by the new mask, which adds one more bit, they'll get the same content. Okay? So this is an easy way to double the size of the ring. So we're going to do a doubling ring. So we have a ring. We're going to have a mask. I'm going to make this a tau. It's not really important how big this is. The important thing is that the mask and the indexes into the ring are big enough that we don't get more than that many entries in the ring. So actually, let's use unsigned. Unsigned mask, unsigned prod, unsigned cons. Okay. So prod will indicate the next entry in the ring that needs to be filled, and cons the next entry that needs to be emptied. So if prod and cons are equal, the ring is empty. Okay. How about full? Well, if they're not, it's not empty, I can do two things. I can either subtract prod and cons, and I can say if the difference is greater than mask or greater than equal to mask, if we want to leave a sentinel element, then we're full. And all of that changes dynamically as we adjust mask. So that's good. This may be all of the data we need for ring. So we have invar. So there's going to be invariance on the Fifo. And this scans the ring. So it is order len in performance and should not be called, well, we don't have len, prod minus s cons in performance and should not be called from within time critical code. Init initializes it to be empty. And I am going to simplify some of the rest of the code by saying, and has some reasonable initial capacity. Okay, FIFO add. Add a given entry on the given given FIFO to call the given function with the given parameter when all the entries added before it have been serviced. Macroize to cast the pointers to the appropriate types. Okay, so FIFO add, we no longer have at. Okay, and here we need to fix the parameter list. Add an entry to the given FIFO to call the given function with the given parameter. And that means I probably should adjust the wording instead to say a given function with a given parameter after all entries with lower taus have been done. Okay. FIFO run 1. So we're going to provide an entry point that just runs the first thing on the FIFO. I'm not sure whether this is if multiple. There is no thing about tau. The FIFO is in its stable configuration when calling the function, which is thus free to FIFO more items. Does nothing if the FIFO is empty or contains. We do not have a bubble. FIFOs don't have bubbles. I don't need them. Repeatedly run items from the FIFO until it's empty. Okay, that works. Power on self-test, built-in self-test, and benchmark. So changes to the header were pretty minimal. So now we seed from the sched file because a lot of the cruft here is going to be boilerplate. So it's set as sched. It's called FIFO. And we have variables called S, which are now going to be called F. Okay. FIFO extend is now FIFO double. Okay. FIFO push to head and push to tail do not exist. We aren't going to do that. Check the invariance on this FIFO and the step at becomes step. It scans the heap, so it is order prod minus cons in performance and should not be called within time critical code. That is still true. Heap is now ring. Cap and len and bubble no longer exist. So we now have mask and prod and cons. These are unsigned. And we will keep those 4 lines in mind for other places. Our assertions. I am going to assert the following. First of all, mask is greater than or equal to 7. I'm going to make my minimum ring size 7. Minimum ring mask is 7. I'm going to assert at the beginning. Oh, actually, this isn't the beginning, so I'm going to assert that prod is greater. Well, prod is unsigned, so it's always going to be greater than or equal to 0. But I'm going to assert that it's greater than or equal to cons. Okay. And prod minus cons is less than or equal to mask. So what we're going to say is we can only differ by up to mask. So we're not going to allow you to fill the ring completely. So if we have a ring that has a mask of 7, you can put 7 things in it. This also means that now we could actually test masking. It means if you mask both prod and cons and they come up equal, it means you got an empty ring because we're not going to allow it to get there. So we're going to assert that ring is not null. We're going to do that first because ring is first in the list of ring, mask, prod, cons. And then we're going to go unsigned from F arrow prod, from prod, not equal to cons. Remember, I is unsigned. It may very well roll around. If we have more than 4 billion things move through a FIFO, we don't want the FIFO to break. We don't have that, and let's see, if I is 0, we don't have that, we don't have that. So now we say if ring sub I dot that at, well, we don't have an at. So now we just use step in var. We did step in var. I think step in var is the only thing we do. Yeah, okay. So that is our invariant checks for the FIFO. So I'm going to turn on all the costly debug options for now. We're going to use these macros in time critical code. And I need that down here because that's controlling whether we call invar or not. So invar itself is not time critical, but efficient. FIFO init. Ring is equal to something. Going to keep some of this up here. So ring is equal to something, and mask prod cons. But prod and cons are easy. They're going to start out at 0. Now mask is start out at minimum ring mask. And ring, let's see, minimum ring size. I need to enforce that this is bits. I'm going to do so with programmatically. 3 size is equal to one unsigned left shifted by bits, and this is going to be size minus 1. So F ring is going to be a C-alloc. Make sure I do this right. C-alloc takes the number of members and the size of. Okay, we're going to do that. And we're going to drop into info fvar invar, and this is going to be, I think we're going to even do this invariant check even when we're not debugging. So that will catch. So for instance, if calloc failed, well, no, let's do that right here. Okay. FIFO add. Add an entry to the given FIFO. We already have a comment on this, which I can copy over. I am starting to get back in the habit of getting my comments right. So FIFO add. Under debug conditions, I am going to call the invariant check. And under non-debug conditions and debug conditions, we are going to grab all of that crap, some of which we won't need. Now, there are conditions where we need to double it. So if prod minus cons greater than or is equal to mask, then FIFO double. Now, once I've done the FIFO double, prod and cons won't change, but mask and ring will. I didn't need ring yet, so we'll move that down there. So we just reload mask. So, is there anything I want to assert here? Well, we don't have to assert anything relating to tau. We've handled changing the size. So now I say ring sub slot, and the slot is equal to mask amper prod. And then we say f arrow prod is equal to prod plus 1. There we have it. FIFO run 1. This function is performance critical. Similar to the above, we are going to gather some of our stuff from F. And I'm going to say if prod equals cons, return. So that's the empty condition. So much simpler. So given that, what we want to do is step run of ring plus mask and cons. Then f cons equals cons plus 1. So question in my mind is, while we are running the function, should I leave the entry on the ring? If I do this, potentially, during the execution of this step, it could produce onto the ring and maybe several times onto the ring, and we could end up invalidating that particular entry. That's fine, because before we call the function, we've already reaped everything we need to know. So by the time we turn over control to the function, it no longer needs that data in memory. So we're going to update cons first. And I'm going to check the invariants before we call and after. So if something in here breaks the invariants, I will know. And because I am a little paranoid, instead of a guard, I am going to make this a if it's not empty, do something kind of a thing. Okay, and run all while prod is greater than cons. Run 1. And this function is performance critical. FIFO double. Double the storage for the ring and then duplicate and copy the original data into both halves of the new, so that the same prod and cons with the new mask point at the same semantic content. Most of this function is performance critical. So FIFO double is called right here, where prod minus cons is equal to mask. So we know that we need to double it. I don't need to think about prod or cons. I do need to think about mask, and I do need to think about the ring pointer. So we got that. Okay, so what we want to do is first we need to establish the, compute the new size and get a new copy set up. So I think I'm going to change this a little bit. There. So CALIC, I'll come back to the idea of optimizing the next thing based on what happens in CALIC. So unsigned new mask is equal to mask left shifted by 1 plus 1, or 1. My habit on CALIC is to always balance the thing on the left with the thing on the right. So next set is to copy the things from the old one to the new one. So mem cpy, destination source. So we're copying to copy from ring and the number of bytes. So unsigned old bytes, actually size t, old bytes is equal to mask plus 1 times size of ring of 0. So we're going to do a byte for byte copy from the ring into the copy, and then into copy plus old old size. Haha. Point arithmetic. Do that mem copy. Now with all that in place, now we can say f arrow ring is equal to copy, f arrow mask is equal to new mask, and we're going to check the invariance. Actually, I think I'm going to check the invariance completely each call, because we only call this when the FIFO has to double in size, which happens a limited number of times on any FIFO. There's that. Push to head is gone. There we go. So all the rest of this stuff is test code. I think I can use the same basic idea. The difference is that I don't actually have a period. So, oops, which argument did I get rid of? So the second parameter goes away. Come on. Sorry, I keep trying to set up a keyword macro here, right? CTX init, find a comma, find the next comma, zap that, and we're done. That's still not going to be correct because we got all sorts of assertions about tau. So Fifo add doesn't have that center one. So we can do the same thing with Fifo add that we did with repctx. Find Fifo, add parentheses, find a comma, find the other comma, and we're good. So post. We're going to add the function, and we're going to check that it didn't run. We're going to run it, check that it ran. All these asserts for tau are going to go away. Just flush all the lines that say tau. So Fifo inc once does not add itself back to the queue. That's correct. So that checks that when we run something that doesn't add it to the queue, we don't keep repeating it. So we're going to go back and do an init again and add the inc once and do a run all. And it should be at 1. Now, before we go any further, I am going to set this up so we actually are calling this. Let's put it before sched. Come on. There we go. So now we are actually going to be exercising this a little bit. So step run of ring was not set here. How about that? P step ring equals F ring. We're going to do that right there. So we get to here and we're saying step invar SFP is not set. So let's take a look at FIFO add. Whoops. Yeah. Debugger time. Let's go right to frame 7. So we're failing the step invariant here, which is being called from here. Index I is equal to 1. And it's all optimized out, so 3 is 0. So, well, part of this is that I'm running the wrong way around the ring. I need to start at cons and run forward until I'm at prod. Yeah. Okay, FIFO invar. I'm getting to something that says prod is greater than cons is being violated. So that could happen if I forgot to write prod, but there I'm writing it. Ah, that is a problem because prod may wrap around. Now, it shouldn't be wrapping around now, so there's something wonky going on. But all these places I say if prod greater than equal to cons forgets that it might wrap. You know what I'm going to do? I think that kind of a test is useful enough. I'm going to change all these to taus. Oops. Those are not really tau. So prod, cons, and mask are all tau things. Separate from that, we shouldn't be hitting that anyway here. So from frame, oops, frame 7 up gets us to here. So we are at FIFO run 1, and we have just incremented cons after the prod is equal to, is greater than, or greater than cons. There we go. I was going one past. So SFP failed. And again, we step down to 7 frames past the crash. So there's the assertion in step. And there's the assertion here. We are testing something in the ring. So I need to turn off the optimizer a bit. so that these things don't get optimized out. Okay, and we make clean. Trigger a build, and we grab it again, and there it's still there. Good. So less things are optimized out here. Interesting that GDB brought that up in a pop-up window. So we're testing the invariant, and we look at F. F says as a mask of 7, prod of 9, cons of 8. And I is 8. Oh, silly me. There. So let's make sure that wherever I am either indexing into or adding an offset to ring, I'm using mask. That's good. So trigger a build, and what I'm seeing is it looks good. Well, it doesn't look great. So that test condition is now failing. Well, that's great because I hadn't really finished up the Fifo test yet anyway. Let's kill the debugger window. So this is saying that FIFO.c got all the way down to here before we had a failure. And that is because this is part of a test that says we're going to run 2 repeating guys with different periods. And the periods are the same now, so what we should see is alternating between CTX1 and CTX2. So start off at the top, add inc once, CTX1 twice. I think I must have merged some contexts here. Okay, so add it twice to the FIFO. Same thing, same context. We run it once, and we haven't run it, it's 0. We run it once, it's 1. We run it once, it's 2. We run it again, and it's not 2 anymore. So this assures that I'm not running it forever and ever. So now we create a new context. Once and once. We do a run all, and we verify it comes up with 2. Okay. And then we add a context where we run this up to 17 times, and we run this up to 10 times. And yeah, let's go ahead and do the invariant checks after each add. Okay, so we've got these 2. Now, the reason why the 17 and 10 was because the other test, this ran at period 10, this ran at period 17, that made them come out. But I think this is still a good test because we can watch what happens to the counters in the end. So, it starts out at 0, verifying that the FIFO add doesn't do anything. And for int I equals 0, right, I equals 1, I less than 5 plus I, we are going to run 1, and verify CTX1 counter is I, and then run 1 and run 1. We're going to verify that the CTX2 counter is I, and then we're going to come down here and we're going to say run all, and we're going to verify that the counters have their appropriate final values. And I think that since I've did a run all here, I don't really need to do the second test of the same thing doing the run all. Okay, benchmark. Literally the same thing. So we're going to do, I think this is the same, yeah, we're going to do the same benchmark we did before. We're going to initialize jobs to 64, but it's going to get mangled down here. And we're going to say initialize a context for each one of these guys and have a different number for each one. This is not the same as the period on the other one, but this will be more jobs will be there in the beginning and they will start to fall off based on that formula. And then we're going to count up the runs and print top. And FIFO ULED, this is per FIFO served step. And this isn't ring size, this is starting jobs. Okay, and I am seeing, remember my problem with the scheduler and how it was really, really slow until I realized I'd left the invariant checking on? Okay, but that means that everything is running with the invariants and it's working. So now I can turn off costly debug options. And I'm not sure why this isn't building. Okay, it's running. There we go. So with the FIFO, you'll notice the heap performance was on the order of log n, where n was the size of the number of pending jobs in the heap. FIFO is order 1. So our performance for the FIFO does not materially change based on the number of items in the FIFO. We are taking on the order of 10 nanoseconds per call, where a subs run takes 3 nanoseconds per call. This is with optimization turned off. So let's turn optimization back on and rebuild and get a decent. I keep forgetting which file that was in. I'm going to go to O2. O2 is a good, it's a good optimization level. O1 to O0 to O1 gets us a lot of performance. O1 to O2 gets us a lot more performance. O3 and OFast, I think OFast is O3, but O3 adds some optimizations that my code is not doing the clever things that those optimizations help out. So O2 is substantially the same as the rest of them. But we're going to go fast anyway. Make clean. Okay, and now we trigger a build. And we see that with the optimizer turned on, interesting that if we only have one job, we are so much faster. Very interesting. Do I have any special case code for consuming the last job or setting the first job? No, I don't. We're starting out with a capacity of 7. I don't know why it's faster at one job. Trigger another run in case that was a benchmarking wart. No, it's true. It's about twice as fast if there's only one job that ever goes in the FIFO. Strange because we get a call that happens and it's going to put itself back on the queue and we have to go all the way back around to the queue consumer, which is going to look back on it. And with 3 jobs rather than 1, the queue shouldn't be knocking the queue out. I'm going to see what happens with 2. Interesting. So if I have just one job, it's fast. If I have 2 jobs, it takes twice as long, but 2 or more all take the same amount of time. Fascinating. I'm going to see if there's a word at Forge. I'm so curious as to what's going on here. No, those really are just stable. What if I let the benchmark run longer? So we're going to run the benchmarks for 10 times as long. So it really does honestly do that. I wonder if there's some fanciness in the CPU where the fact that we just wrote that location, even though the next one is only a few words beyond, reading it back is faster. These should all be in the level 1 cache. Oh well. Okay, so we'll just ignore the fact that the FIFO is really fast with one job, or at least note it as a weirdness, and we will budget 5 to 10 nanoseconds per job when we go to the FIFO. It's pretty stable at 6 to 7, actually. Okay, so we're back at our shorter benchmark runs. It's still quite stable. So a empty heap and an empty FIFO are pretty close in performance to each other. They both go up at 3, but after that, the heap starts going up further and the FIFO just stays there. So we now have our FIFO structure. And that's good because that means that we can recognize that I am listening to a signal with a lot of other people listening to it, and I don't want my outputs to be handled until all of them are done. So I could have a system FIFO that I can toss things in that says, when you're done running all of the current edge triggered things, go service the FIFO. Also means that my main loop, if I've got a recycling, do this, then do this again, then do this again, that can go on the FIFO. So it, as long as it puts itself back on the FIFO when it is done running, what we'll do is we'll call that, it will do stuff including triggering edges, and those will trigger other edges, and some of those will put it on the FIFO, and we'll come back and we'll do the rest of the things that are on the FIFO before we do the main clocking again. There we go. There's our clocking. And somehow that would need to synchronize with the scheduler, which is coming up at some point. Yeah, when we design our main loop, we need to think in terms of how do we assure that we don't execute when we're taking from the scheduler, if we have something that is producing a clock at a steady rate, and it's increasing tau, and then we've got the scheduler stuff. I don't want my fundamental clock to be on this scheduler heap because this is slow. So we're going to have a main loop that just calls that fundamental clock over and over and over again, but it will need to monitor the schedule heap to say, oh, I need to call him. I need to call him again, which means that our heap will need to provide us with some things. That's further down the road. So is bench done? Excuse me, is FIFO done? I think FIFO is done. Let's get into log and let's look at the live coding log. And we've got all of this information about FIFO and sched post are printing, nobody else is. So let's ditch those. Potentially, I'm going to have a lot of modules that have these things. We're already getting a bunch of them. And the more we get, the more noisy it is to have each one of them say top, end. So we're going to reserve top and end for things we print in whatever it is we're working on right now. So we see there we've killed top and end, and we need to go back to the log and remove the expected here. Okay, so our benchmarks are beginning to take significant time. So I think along with checking in FIFO, I'm going to recognize that and adjust main. So now in main, we're going to have a loop at the top, which is going to go do things based on our argument list. Actually, I always run main post, period. So now if I have bist, I'm going to say main bist. And if I have bench, I'm going to say main bench. And then we're going to return like that. So by default, if we just run the code, it's going to do main post. If I have arguments that say bist or bench, it will run them. In fact, I am going to, yeah, I'll just do it that way. Else. Fail. Unrecognized parameter request. So if I do that, now I want to change my build rules. So the run log is still just the post. Is it going to be post or is it going to be bist? That's going to be the bist test. So run log, and then we're going to have the benchmarks, which are run separately and aren't going to be sent out to standard error. I just realized the way I've written run here, it's going to do it twice. So yeah, if I have a run, I'm going to do it that way. So now instead of, let's see, loop, it says make compare. And if make compare succeeds, then I'll do bench. $C, $inst, bench. Hold on. Bench, no such file or directory. What? There should be inst in here. Exec. I changed a convention and didn't follow through. Okay, so so make logs is no longer going to be printing the benchmark results. That's not good. So what I want to do inside this window is make logs bench and format. So bench will depend on successful difference check. So every time I hit a G there, it's going to dump the logs, and if we had a successful check, we're going to run the benchmarks, and if that's good, we're going to do the format. And this can be checked in. And I think an hour is a good length for this, so I will go work on checking this in off stream. And I hope to talk to you all soon in the next one, where we will get started coding. Well, let's see, the next thing. Let me think. What's likely next? We'll have our FIFO. We have our queue. We need a time base for the system. So we can say, I need a clock running at 18 megahertz, and I want a signal coming out that transitions, and I want a tau that's increasing, and I want something that relates back to, okay, given this tau, this is my microseconds since the start of the simulation. And the purpose of that will be to wiggle an edge, wiggle a signal with an edge. So that will require an edge. An edge requires a current state for the signal, the ability to make it high or low, the ability to subscribe to rising and falling edges, and to dispatch to those when the value changes from low to high or high to low. I think edge is our next thing. So we'll come back on the next session to do edges. Well, have fun and keep your code safe. End stream.